Have you ever tried to fix something, like maybe a problem at work or even just something around the house, and your exact attempt to fix it just completely tears the whole system apart?
Oh, absolutely. I mean, it
Yeah.
happens all the time, right? You end up making it way worse.
Exactly. And well, today we are doing a deep dive into this incredibly fascinating, almost philosophical battle over how to manage chaos.
It really is a battle.
Yeah, it is. Because on one side, you have this very traditional approach, hunting down a root cause to permanently eliminate a problem.
Right, the classic fix.
But then on the other side, there is this highly controversial science of continuous compensation, basically just constantly tweaking the thermostat to survive a messy, unpredictable reality.
Which is how a lot of the world actually operates.
It is. So today's mission for you, our listener, is to explore the statistical frameworks of how modern industries actually manage these massive, complex systems. How do they keep things running perfectly on target when literally everything is trying to drift off course?
And, the stakes here are just massive.
Oh, for sure.
Because we are operating in environments that are just defined by information overload.
Yeah,
Right?
yeah.
Endless, continuous variation. And if you don't understand how to properly steer a system mathematically,
It just crashes.
worse. You don't
Yeah.
just fail to improve it. You actually amplify the chaos. Your attempts to correct the drift become the actual source of the turbulence.
Wow. Okay, so to get into this, we are looking at Chapter 12 of the textbook Introduction to Statistical Quality Control, 6th edition.
It's a classic.
It is. Sounds like a dense engineering manual, but it really outlines this clash between two rival schools of thought. First up, we have SPC, or Statistical Process Control.
Right, the traditional heavyweight. Yeah.
Yeah. And SPC is built on a framework of hypothesis testing. It's very top-down. The foundational assumption here is that a process can and absolutely should be brought into a state of perfect statistical control.
Yeah, it assumes perfection is possible.
Right. So you observe normal random variation and you just leave the system alone. But the second your control chart shows a beta point outside the normal limits, you sound the alarm.
You stop the line entirely.
Yep, you stop everything, you find what they call the assignable cause, and you kill it.
Exactly. The focus with SPC is entirely on identifying a specific reason things went wrong.
Like a broken gear or something.
Yeah, a bad batch of raw material, a worn-out tool, maybe some weird environmental anomaly. SPC demands that you find that root cause and eliminate it permanently. It's got a long history in discrete parts manufacturing, making individual widgets.
Right, making a car door or screw. But then we have the rival school, EPC.
Engineering process control.
Yes, EPC. And this operates on a completely different core assumption. Okay.
Totally different.
Mhm.
It assumes that despite your absolute best efforts, a process is naturally going to wander away from its target.
Because there are just, endless unknown environmental forces, inertial shifts that you simply cannot isolate.
Right, you can't put everything in a perfect vacuum.
Mm-hmm.
EPC is mostly used by engineers in continuous processes. Think chemical plants, oil refineries, stuff that flows.
Okay, so EPC deals with the reality of that drift tactically. Instead of launching some massive investigation for a root cause that, frankly, might be economically impossible to fix.
Right, you can't just shut down an oil refinery to find a tiny anomaly.
Exactly. So EPC uses parameter estimation and feedback adjustment. It constantly measures how far the output has wandered off target, and then it tweaks what they call a manipulatable variable to nudge the output back into the sweet spot.
It is a philosophy of continuous, calculated compensation.
Okay, let's unpack this with a practical example. Is SPC like trying to find and seal a drafty window to fix the temperature in your house once and for all?
I like where this is going.
While EPC is just, accepting that the house is inherently drafty and constantly turning the thermostat up and down to compensate?
That analogy perfectly captures the friction between these two methodologies.
Oh, awesome.
Because what's fascinating here is finding the drafty window, the assignable cause, that is the ideal permanent fix.
Sure, officer.
But the problem is that in highly complex systems, locating that single draft might be impossible. Or replacing the window might require shutting down a multi-million-dollar operation for 3 days.
Right, which the company won't let you do.
Exactly. Turning the thermostat up and down, though, keeps the environment stable right now in the present moment. These techniques grew out of entirely different environments, but they share the exact same ultimate goal.
The reduction of variability.
Yes, the reduction of variability. But their mechanisms are, Entirely opposed.
So to actually steer this drift, to keep the thermostat balanced, engineers rely heavily on a mathematical technique called integral control.
Yes, integral control.
And it's called that because it literally integrates or sums up all the past errors the system has experienced to figure out where the process is going to wander next.
Right, it looks at the history to predict the future.
And it relies on a forecasting tool called an EWMA, an exponentially weighted moving average.
The mechanics of an EWMA are just so powerful. Rather than treating all historical data equally, an EWMA assigns a weighting factor.
Represented by the Greek letter lambda, right?
Yes, lambda. And it uses lambda to decay the memory of older data.
Hmm.
So the current forecast is calculated by taking the previous forecast and adding lambda multiplied by the current error.
Okay, let's make that concrete for everyone listening. The lambda determines how, sensitive or paranoid your system is.
That's a good word for it, paranoid.
Yeah, so the textbook notes that an educated guess for lambda for a stable, responsive system is generally setting it somewhere between 0.2 and 0.4.
Right. And if you set lambda to 0.2, you are basically telling the mathematical model to assign 20% of the decision-making weight to the most recent data point.
While the remaining 80% is anchored in the historical inertia of the process.
Exactly. As data points get older, their influence exponentially fades into the background. A lambda in that 0.2 to 0.4 range is a beautifully robust sweet spot. It almost always works wonderfully.
Because it reacts fast enough to catch a genuine drift, but sluggish enough that it won't freak out over a random blip.
Spot on. It won't overreact.
So we can see this play out in an example from the source material, example 12.1. There's a chemical process creating a polymer. And the goal is to keep the molecular weight of this polymer at a precise target of 2000.
But the weight is inherently unstable.
Right, it's drifting all over the place, completely out of statistical control. The standard deviation is 19.4.
Which is huge.
Yeah, so the engineers step in and they apply integral control using an EWMA with a lambda of 0.2. They forecast the drift, and to compensate, they constantly tweak their manipulatable variable.
Which in this case is the feed rate of a chemical catalyst.
Exactly. And the results are wild. By adjusting that catalyst feed rate, they slash the standard deviation of the polymer's molecular weight down to 10.35.
That is nearly a 50% reduction in variability.
Just by applying that continuous mathematical steering.
It's incredible, but there is a catch.
Yeah, here's where it gets really interesting. Because if you look at the raw data of this intervention, a massive philosophical issue emerges.
Right.
The molecular weight of the polymer gets beautifully smooth and stable, but the catalyst feed rate, the variable doing the steering, it looks like a seismograph during an earthquake.
It is swinging wildly.
Right. It's all over the place. So wait, if we are just taking the chaos from the molecular weight and transferring it over to the catalyst feed rate, isn't that just cheating? We haven't solved the chaos. We just hit it in another variable.
This raises a really important question, and something a lot of people struggle with at first. But that transfer, that is a deliberate strategic trade-off.
Really? Just moving the mess around.
Yes, and it's fundamental to how engineering controllers function. You have to evaluate what the end customer actually cares about.
Okay.
The client buying the polymer requires the molecular weight to be exactly 2000. They do not care in the slightest how violently you had to open and close a catalyst valve in your factory to achieve that state.
Oh, I see. As long as they get what they paid for.
Exactly. As long as the physical and economic cost of adjusting that manipulatable variable is negligible, and turning a valve generally is, transferring the variability is a highly effective, totally acceptable engineering solution. You move the chaos from a zone where it causes catastrophic failure to a zone where it is harmlessly absorbed.
Wow. Okay. Moving the chaos to a safe container. I love that. But that completely relies on the assumption that the system was actually drifting in the first place, right?
Yes. And that brings us to a massive danger, a pitfall called the tampering trap.
Popularized by W. Edwards Deming.
Right. Deming warned about this constantly. If your process is already stable, meaning it isn't drifting, it's just experiencing normal, random statistical noise.
So the true lambda driving the disturbance is effectively zero.
Exactly. If the true lambda is zero and you try to apply EPC to steer it anyway, you completely destroy the system.
You make it worse.
Much worse. The mathematics of tampering are totally unforgiving. If you apply an integral controller to a system that is already in perfect statistical control, you mathematically double the variance of the process.
So to double it.
Yes. Your adjustments literally become the source of the chaos.
Okay, so it's like driving a car on a perfectly straight highway. If there are tiny random variations in the road surface or a slight crosswind and you just hold the steering wheel steady, the car stays safely in the lane.
Right. That's a stable process.
But if you hyperfixate on every single millimeter the car naturally drifts within the lane and you violently jerk the steering wheel left and right to fight the wind, you are going to send the car careening all over the road.
That's a perfect analogy. You are reacting to noise as if it were a signal. And because an EWMA is always looking backward at past errors to calculate its next move, oversteering based on random noise creates this oscillating feedback loop.
You push the process off target and the EWMA sees the error you just created and overcorrects in the opposite direction.
Exactly. You are fighting ghosts and creating monsters.
That is terrifying. So knowing when to steer and when to just sit on your hands is critical.
Absolutely.
And that requires translating all this complex forecasting math into simple tools. Tools that human operators on a factory floor can actually use because, most operators aren't doing exponential decay calculus in their heads.
Definitely not. So when a system lacks automatic process control, meaning computers aren't just making the adjustments automatically in the background, engineers have to design manual interfaces for the humans.
Right.
And the most elegant solution for this is the Box-Jenkins adjustment chart.
Okay, let's talk about these charts. Because they map the relationship between the output you care about and the variable you are manipulating, using two inverted scales side by side.
Right, based entirely on the mathematical process gain between the two variables.
So going back to the polymer, let's say a 6-unit increase in the molecular weight naturally requires a 1-unit decrease in the catalyst feed rate to bring it back to target.
The chart basically places the scale for the polymer weight right next to the scale for the catalyst feed rate, inverted based on that exact ratio.
So if the operator pulls a sample and sees the polymer weight has hit 2006, they don't perform a single calculation.
Not one. They locate 2006 on the first scale, look straight across to the adjacent scale, and the chart simply reads -1.
And they instantly drop the feed rate by 1 unit.
It is brilliant. It turns dynamic forecasting into a static visual lookup.
But making an adjustment every single period, that creates a massive amount of physical friction, right? Turning a valve might be easy, but in a lot of places, making an adjustment requires briefly stopping a machine, resetting a tool, or pulling an operator away from another task.
Yes, and that physical and economic friction is exactly why bounded adjustment charts were invented.
Bounded charts.
Right. Intervening continuously is financially devastating if the cost of the adjustment outweighs the cost of the product being slightly off target.
Makes sense.
So a bounded chart introduces calculated limits, usually noted as plus or minus L. You observe the drift, you calculate the EWMA forecast, but you do absolutely nothing until the forecasted error breaches those specific limits.
Okay, so it's exactly like putting bumpers in a bowling alley lane.
Yes.
Instead of micromanaging the bowling ball's path every single inch down the wood, constantly nudging it left and right to keep it perfectly centered, you just let it roll.
You tolerate a certain amount of drift.
Right. You only intervene and bounce the ball back toward the center when it physically hits the bumper and threatens to go into the gutter.
I love that analogy. And the economic efficiency of those bumpers is staggering. The textbook gives an example where, in a highly volatile process, an operator using a continuous manual chart might have to make an adjustment 50 times in 50 periods.
That sounds exhausting.
It is.
Yeah.
But by implementing a bounded chart with limits perfectly calibrated to balance the cost of being off target against the physical cost of making an adjustment, that same operator might only need to intervene 5 times over those same 50 periods.
Wow, from 50 down to 5.
Yeah, and here's the crazy part. Those 5 strategic interventions are still enough to slash the overall variance of the final product by 50%.
That is wild. You achieve the vast majority of the stability for a tiny fraction of the operational friction.
It perfectly balances the costs. Also, real quick, there are rounded adjustment charts too, which simplify things even further by creating zones, like a +1 zone, a -1 zone, or a central do-nothing zone.
Right, keeping it simple for the floor. But eventually, systems become fully automated, right? And engineers move beyond just integral control. They start implementing PI and PID controllers to handle the steering.
Yes. PI stands for proportional integral, and PID adds derivative control.
Let's break those down, because they are basically the backbone of modern industrial automation, right?
They are. And they work by dissecting an error into 3 distinct temporal phases: past, present, and future.
Okay, so the proportional component, that reacts to the absolute size of the current error.
Hmm.
If you are driving and you suddenly see you are drifting out of your lane, the proportional response is how hard you pull the wheel, based purely on how far over the line you are right now.
Exactly. Current error. Then, the integral component, as we discussed, is looking in the rearview mirror. It sums up the past errors to catch slow, creeping drift that the proportional control might ignore.
Like, if you've been slightly under the speed limit for 10 miles, the integral component recognizes that accumulating error and slowly adds gas.
Spot on. And then there is the derivative component, which looks at the slope or the speed of the error.
It's essentially an accelerometer.
Right. If the gap between you and the car in front of you is closing incredibly fast,
Hmm.
the derivative control senses the rapid rate of change and hits the brakes aggressively, long before the gap actually disappears.
Ah, so it's entirely designed to prevent overshooting.
Exactly. If the system is rushing back toward the target too quickly, the derivative component applies the brakes to soften the landing. It prevents the process from blowing right past the target and oscillating out of control on the other side.
Okay, so you have this perfectly tuned PID controller executing brilliant continuous steering. Sounds flawless, but pure EPC has a fatal blind spot, doesn't
A
it?
massive one, yeah. It is completely blind to the underlying health of the system.
It never looks for the root cause.
Never. It is fantastic at reacting to upsets and keeping the output on target, but it never asks why the upset happened in the first place. It just blindly compensates.
So if we go back to the driving analogy, EPC is constantly adjusting the steering wheel to stay in the lane. But if you try to drive using only SPC, only looking for root causes, you wouldn't steer at all.
Right. You would just hold the wheel perfectly straight until the statistical evidence of your tires hitting the rumble strips proved you were out of control.
Meaning you'd crash.
Yeah, and then you would pull over to investigate the assignable cause of the crash.
Obviously a catastrophic way to travel. You need the continuous steering of EPC just to survive the journey. But what happens if you are driving and your front right tire suffers a massive blowout?
Well, the car violently pulls to the right.
Right. And what does EPC do?
A pure EPC system would instantly calculate the deviation and blindly pull the steering wheel hard to the left to compensate.
So the car stays in the lane, the output looks perfectly stable to anyone watching.
But the car is being destroyed because you were driving on a shredded tire and the system never stopped to fix it.
Wow. Okay, so what does this all mean? How do we fix that blind spot?
This is where the two rival philosophies must finally merge into what is known as algorithmic SPC.
The ultimate system.
Yes, you use EPC to continuously steer the process to keep the output on target and absorb the daily chaos. But simultaneously, you run a classic statistical process control chart.
But the genius is where you place that chart, right? You do not monitor the final output.
Because the EPC controller is already masking the chaos there.
Exactly. So instead, you run the SPC chart on the control errors, or better yet, on the adjustments themselves.
Yes, you statistically monitor how hard the system is having to fight the steering wheel. As long as the adjustments the EPC controller is making stay within a normal historical range of variation, you let it steer.
But if the system suddenly has to crank the manipulatable variable way outside its normal bounds just to keep the output steady.
The SPC chart catches the anomaly and sounds the alarm.
Okay, let's bring it all together with example 12.2 from the text. The polymer process gets hit by a massive assignable cause at period 60. Some catastrophic failure occurs in the background that naturally spikes the molecular weight by 25 units.
The EPC integral controller immediately senses that upward drift and fights it. It aggressively cranks the catalyst feed rate valve wide open to force the weight back down.
And if management is only looking at the final polymer output, everything looks totally fine, right?
Completely fine. The EPC controller manages to absorb the blow and keeps the standard deviation at an acceptable 15.4. The car is still in the lane.
But the operator monitoring the algorithmic SPC chart sees that the catalyst valve has just been pushed to an unprecedented extreme. The EWMA control chart monitoring the adjustments triggers a massive alarm at period 70.
Right. The statistical evidence proves this isn't just normal environmental drift anymore. Something has fundamentally broken.
And because the alarm triggers, the engineers know it is time to stop treating the symptom and start hunting for the disease.
They investigate, they locate the specific root cause that spiked the system, and they permanently eliminate it.
And the moment they kill that root cause, the standard deviation of the final product drops even further, down to an incredibly tight 10.8.
The process isn't just surviving anymore. It's truly optimized.
If we connect this to the bigger picture, EPC keeps the patient alive and breathing, while SPC acts as the diagnostic alarm that tells the doctor it's time to perform surgery and remove the underlying disease.
Beautifully put. You absolutely need both methodologies functioning in tandem to create a robust, optimal system.
Well, we have covered a massive amount of ground here today. From the rigid binary logic of SPC hunting down broken components, to the fluid mathematics of EWMA forecasting and PID controllers, constantly tweaking the manipulatable variables.
In the economic efficiency of those bounded adjustment charts.
Yes, the bowling bumpers for the floor operators. And ultimately, how monitoring the steering effort itself with algorithmic SPC protects a system from literally destroying itself.
It really is a profound masterclass in balancing intervention with observation.
It is. So to wrap up, I want to leave you with a final thought. Take this whole framework, Chapter 12, and apply it to how you manage your own personal life and productivity.
Oh, that's interesting.
Yeah, think about it. When things get chaotic and you start falling off track, which framework is dominating your reaction? Are you strictly locked in an SPC mindset?
Waiting for the breakdown.
Right. Do you ignore the creeping fatigue and refuse to adjust your daily routines until you hit a wall of total burnout, forcing you to completely overhaul your life to find the root cause of the crash?
Refusing to steer until you hit the rumble strips.
Exactly. Or, on the flip side, are you trapped in an endless EPC loop?
The tampering trap.
Yes. Are you constantly tweaking your daily manipulatable variables, chugging a third cup of coffee, shifting deadlines, aggressively managing your schedule hour by hour, just desperately fighting the drift to maintain output?
Blindly cranking the steering wheel to compensate for a flat tire.
Without ever stopping to ask why your system is generating so much friction in the first place. So how could you build an algorithmic SPC system for your own personal workflow? Give yourself the grace to make those daily bounded steering adjustments to survive the messy reality of a given week.
The bumpers.
The bumpers.
Okay.
But critically, establish a clear statistical alarm for yourself. Monitor how much effort it is taking just to stay in the lane so you know exactly when it is time to stop compensating, look under the hood, and finally fix the root cause.
That is a powerful way to look at it.
Keep questioning your systems, keep refining your variables, and we will see you next time.